finally, let's do an example. So the following data are some observations of classroom temperatures and mean test scores for 5 sections of Math 1530, the freshman statistics course we teach here at Austin Peay. You see, a few years ago, a couple of my colleagues and I decided to carry out a really mean experiment. Like I mentioned previously, oftentimes designed experiments can be real powerful ways to detect causal relationships. However, sometimes they're very unethical, as in this case. So what we did here was we had 5 classes between us, and when it came time for final exam, we set the thermostats to 5 different temperatures in these 5 different classrooms, and we observed the average exam scores. What do you notice here? Is there a trend? It looks like as the temperature increases, the average exam score is decreasing, right? The average exam score is decreasing. That sort of makes some sense, I guess, right? I mean, the hotter it is, I know it's harder for me to think when it's hot. Well, let's build a regression model here. So I've already put these values into a couple of lists in my calculator. Again, the first thing I always do is I try to decide which one of these variables should be the independent variable or explanatory variable, and that's probably temperature, right? You're looking to see if temperature has an effect on this response, which we call the score. So I've got my temperatures here in list 1, my exam scores here in list 2. So you should take a moment to put those numbers into your lists like that into your calculator. Now what I'm going to do is mainly use the full functionality of my calculator to get R and also something called R squared and the regression coefficients. So we already know how to do that, right? Press stat. Press the stat key right there, stat, 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 and then arrow over to calc, option 4. Remember, you can use option 4 or 8, doesn't matter, you just have to know how to read. I'm going to choose option 4 because I like 4, and my X list is list 1, my Y list is list 2. Don't have a frequency list. I'm going to store the regression line equation by I hit vars, Y vars, enter, enter. Remember that? Let's do it again just for practice. Vars, Y vars, enter, enter, just like that. And then go down to calculate, and guess what? It's going to calculate my regression coefficients. Oh, guess what? My calculator reset for some reason. I've got to run that diagnostic on command again. So if you missed this in a previous video, well, here's what you have to do. Second, catalog, and then go down to the D's, okay? Arrow down to where it says diagnostic on. Diagnostic on, and you run that sucker. Now, if I go back and do stat, calc, lin, reg, option 4 there, and do all this same stuff, I should get all the output that I'm looking for. Voila, there it is. A, here is my slope. Now in the notes, I use the symbol B1 for the slope. Okay, and I used the symbol B0 or B0 for the intercept. It doesn't matter what symbols you use. I can tell by looking at this slope-intercept form of the line right here that A must be the slope because it sits right next to the X, and B must be the Y-intercept because it's over there all by itself. Now I'm going to write down this equation with my pen. I'm also going to include the original units because that's going to make the equation much more meaningful. So what's your response? It's predicted exam score, right? So that's what I'll say. I'll say exam score, and it's estimated, right? So I'll put a hat over it, equals negative 1.4546. And that number has some units on it, right? Slope always has mixed units, right? Rise over run units. The rise units, or response units, are percentage points. And the run units are degrees Fahrenheit, right? And then my X variable, I could put an X there, or I'm not going to do that. I'm going to put exactly what it is, just the temp, the room temperature. And then my y-intercept there is 182.8822. That's positive. Great. This tells me a couple of things right off. I mean, well, first of all, again, the main utility is that if this regression line is of any use at all, then maybe I could use it to predict the average exam score for a class based on the temperature in the room. It also tells me right off, hey, look at this. What happens if the temperature is set to 0? If the temperature is set to 0, then all of this stuff goes away. So it says that for 0 degrees Fahrenheit, we could predict an average exam score of 182.8822. Guess what? That's called extrapolation, right? Because we didn't observe any temperatures down in and around 0. All of our temperatures were up between like 68 and 80 or so degrees. I don't think we could get the room that cold. So right off, I can see that. Also, right off, I look here at the slope. What is the meaning of the slope? It says that for every 1 degree temperature, it says that for every 1 degree of temperature increase on the Fahrenheit scale, the average exam scores seem to be dropping by about, dropping, that's the minus sign, dropping by about 1.45 percentage points. So when I plot this, I should see a trend line going like this, where the slope is this, and then this guy would be my y-intercept. Okay, so in fact, let's do that. Get my calculator back out here, and so now if I go to second and stat plot, and I'll turn one of these plots on, and I want to make a scatter plot like so. I've got my list 1 and list 2 in there the right way. Again, it's real important that you get your independent variable or explanatory or predictor variable there as your X list, and your response variable or dependent variable there as your Y list. And I'm going to hit zoom 9. And there we go. Yeah, there are data points, and hey, that line looks like it runs pretty much right through those data points. I can hit the trace key and bounce around those points. Yeah, so sure enough, I see my graph looks like this. But this is not the origin down here, right? Down here in my graph, this corner down here is not the origin. And that's okay. So that begs the question then, how would you expect the average exam score to behave over a larger temperature scale? Okay, like if we had 0 down here, would it really stay linear like that? You know, we've got these data points that are down in here, you know, is what we've observed. You know, this line says that the y-intercept is right, you know, right there. No, this line is probably a pretty bad model. I don't know about you guys, but I can't think very well and perform very well on an exam if it's too hot or too cold. So I bet, you know, the actual trend would probably look something, you know, more like this. Probably sort of more parabolic or concave downward. So in this case, a straight line model is not really sufficient. And if you go on to take more statistics courses, you'll almost certainly see some curvilinear regression. So I'll tell you what I'm going to do at this point. I'm going to actually work out these regression coefficients sort of by hand using those formulas that we know. That is that the slope is supposed to be r times standard deviation in the y values over the standard deviation in the x's, and that the y-intercept is supposed to be y bar minus b1 x bar. I will use my calculator to aid me a little bit here. I've already got r, it's right there. I'm also going to need the standard deviations and the sample means. So I can get all that stuff real quick by using my calculator, right? If I go to stat and calc and 2 variable statistics, because I have 2 variables, right? I've got an x variable and a y variable, and then I'll just, you know, so I enter the appropriate list there. Don't have a frequency list. Calculate. There we go. X bar is 73.34. And the standard deviation of the x's, that is the sample standard deviation for the x's, is 2.834254752. The standard deviation in the y's is about 4.147288271, and the average of the y values is about 76.2. Now all these numbers have units on them, right? Well, the r value doesn't have units. The standard deviations and means have the same units as their original variables. So the standard deviation in the x's has units of degrees Fahrenheit, and so does x bar. And then the standard deviation in the y's has units of, say, percentage points, and the average y value also has units of percentage points. So now if I plug into my calculator, if I take my r value, negative 0.99408978819, multiply by the standard deviation in the y's, 4.147288271, and then divide by standard deviation in the x's, 2.834254752. I get, there we go, negative 1.4546 or so, which is just what your calculator got. Now remember, we have rounded some in our calculation here in the calculator, so it might not be exactly like what the calculator got, but it ought to be pretty darn close. And finally, how do you get B naught? It's y bar minus b1 x bar. So y bar is 76.2, and then minus b1, I'll put that in parentheses just so it doesn't get too confusing because I've got that minus sign there. And then times x bar, the average of the x values, was 73.34. And there we go, 182.88. That's what we got approximately, okay, for the y-intercept up here. Now let's see real quick how to do this with Minitab. So in keeping with my convention, I'm going to put my x values in a list on the left and my y values in a list on the right. But I'm actually going to call them what they are. My x values are my temps, and my y values are my exam scores, or average exam scores rather. And my temps are 69.1, 72.3, 73.9, 74.8, and 76.6. And my scores are, let's see, I got an 82, and a 78, and 76, and a 74, and a 71. Okay, so there are several ways you can do this with Minitab. I'm going to go up here to Stat and go to regression. There you go, regression. And oh, how about this? Fitted line plot. This will get me a fitted line plot. Let's try that. My response is the scores variable, and my predictor variable is the temperature variable. Hey, look at this. You can do linear or quadratic or cubic. These are curvilinear models, but let's just stick with the linear model for now. I'll click OK. And there you go. It gives me a nice plot with the data points. It's all in color and stuff. That's pretty cool. So here's the r² value. Again, we don't know what this means yet, other than the fact that it is the square of r. We'll be talking about that soon. And again, up here at the top is our regression line equation. They put the y-intercept on the left, and that's just fine. 182.9 or so minus 1.455 times the temperature. Very good. You can also see some output in the session window here. It says the regression equation is this. Scores equals, and by scores they really mean scores hat, okay? 182.9 minus 1.455 times the temps, and they've rounded a little bit more than I like to see, but so yeah, that's what they have there. And here's the r² value, and here's some other stuff that we don't need to worry about, but it's called analysis of variance table. Now, I tell you what, I'll go back to the regression line equation that I got here. The slide says, could you use the regression line to predict the mean test score when the temperature is, say, 70 degrees Fahrenheit or 72.5? Well, sure. And how do you do that? Well, it's so simple. You just plug in, right? I get, let's see, my regression line equation is, I get negative 1.4546. And so when the temperature is 70 degrees Fahrenheit, okay, I just plug in there, right? Times 70 degrees Fahrenheit, then plus 182 point, what was my y-intercept? 8822. You see that? I just plopped the 70 in there for, where my explanatory variable is, temp. That's all there is to it. That's how you can use it to make predictions. So I'll press enter. There you go. 81.06%. Okay. What about if the temperature was 72.5? Well, let's just do second enter, and pulls up what we had before, and I'll go back in here and I'll change that 70 to 72.5. So I get 72, and then I got insert, so second delete. See that for the INS there for insert, 0.5. Okay, now press enter. Good. Yeah, it's a little bit lower, right? As the temperature seems to increase, it seems that our average exam score is decreasing. So I would predict that when the temperature is 72.5 degrees Fahrenheit in the room, that the average exam score may be more like 77.42. So what about when the temperature is 100 degrees? What if it gets really hot? 37. Whoa, that's not good at all. What if the temperature was, gosh, and I hate to think about it, but what if the temperature got to be like 199 degrees? It's probably never going to happen. But gosh, what if it did happen? Oh, holy smokes, a negative exam score? I don't think so. So again, that's extrapolation in the other direction. You want to be real careful about that. You can't make predictions on the response variable based on values of the explanatory variable that are outside of those that you've made observations on previously. It's just not going to work very well. It's dangerous. And again, we've already interpreted the slope and the y-intercept. We said that it's essentially the slope here. It's negative 1.4546 percentage points per degree Fahrenheit. What that indicates is that for every 1 degree Fahrenheit increase, right, as I run to the right 1 degree Fahrenheit unit, my predicted exam score is going to fall because of the minus sign there. It's going to fall by about 1.4546 percentage points. And my y-intercept, what this just means is, it's a quick way of saying, hey, you know what, if the temperature is 0, then this is what we would expect our average exam score to be. And of course, this doesn't make sense. Now, is this model any good? Well, yeah, it might be okay in this local region for temperatures between, say, I don't know, maybe between 65 and 85 degrees.